opportunity to think about crazy stuff and propose it. But we can also aid in evaluating it, right? So it's not, it's not our privilege to just, have fun. We should also try to help out in evaluating crazy stuff. Does it make sense? All right. So I have a few advice to academic researchers, and this is presumptuous, I know, right? So why am I allowed to give advice here? But I will do that anyways because I'm on stage. Okay, so academic researchers could be in the ivory tower. It's the model that, academics sit and they talk to other academics and they don't care about the surrounding world. That's one model. The other model is to do industrial relevant research with all its complications, right? With all the constraints, you can't do this, you can't do that because then this breaks and blah, 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 right? Nothing is possible in this world. So of course, we cannot be in either of these two sides because then there will be zero progress. Okay? So we need to know in which lane we are, and we also need to know when it's time to switch. Of course, we need balance. Right? But again, my advice to academic researchers is to spend a little bit of time in the ivory tower, right, to try out crazy stuff. But every now and then, you also need to go out in the real world and meet the people that actually are supposed to implement this. And if we do that in an effective way, we will have a great 7G. If we don't do it, we will have a bad 7G. Okay, more advice to researchers. And here I think we as a community, we can improve. So our research for all should be open, right? And this is more important now than ever. With open, I mean it should be published, it should be peer-reviewed, it should be discussed. We also need our research to be reproducible, okay? And the funny thing here is if you ask your friendly ChatGPT to do an image here, it produces something which is not reproducible. So this stamp will not produce this imprint. You see the problem? Yes. All right. So that's AI research for you, right? Or when you let an AI do research for you. And secondly, it should be rock solid. I have very little tolerance for sloppy work, okay? I understand that there is a paper deadline. I understand that you need to graduate. I understand this. But that is not an excuse to be sloppy, right? Because the more noise we have in our academic publications, the harder it is to find the truth. And truth is what we all are about. Okay, so that was very presumptuous, and let's go to something a little bit more technical here. So spectral efficiency, we all love it. We all want to maximize it. Okay, so here we have a PhD advisor and a PhD student. The PhD advisor to the left is a real person. The PhD student to the right is a ChatGPT person. But anyways, the person to the left says, you want good spectral efficiency? Well, it cannot be more than the log 2 of 1 plus p over n. And then the PhD students say, great, now I know what to do. So, which problem should I actually solve? Should I solve this problem to maximize the spectral efficiency such that the transmit power P is less than P max? Or should I solve this problem? Minimize the power such that the spectral efficiency is above a certain threshold. So I'll let you think about this for 5 seconds. Which one would you recommend the PhD student to study? The left problem or the right problem? Both? That's a safe bet, right? Yeah. Okay, but if we look to the left and then generalize it, it's to maximize performance such that the resources we use is less than the maximum resources available, right? That you can see many optimization problems as this, right? or many research problems. Or the other one is to minimize resources such that performance is good enough. And I claim that if we do the left, we will end up here. It's not sustainable. If we do the right, we may end up here. Not sure though. But I mean, when setting up the specific problems to solve, we should think about this, right? The game is not to maximize performance. The game is to provide good enough performance. Yes. All right, so that was presumptuous. Let's be a little bit more technical. Machine type communication, we all love it, and we want to optimize it. So machine type communication comes in two big flavors. One is ultra reliable, low latency communications. URLLC is possibly the worst acronym ever, especially when you want to say it fast. I challenge you. All right. So here we see such a use case of a satellite. It gets some commands from Earth to change its orbit. Okay, that's a pretty critical type of communication scheme, right? You want to conserve the fuel of the satellite, and you definitely don't want it to be inoperable, right? The other one has to do with massive machine type communications, where a single node, a base station, is connected to millions or tens of millions of devices, perhaps. Slightly better acronym, but not great. Okay. So, mobile broadband in general relies heavily on long packets. Okay, so IP packets, maybe 10,000 bits, 12,000 bits, or something like this. However, control traffic and some machine type communication relies on short packets, where the payload is hundreds of bits, maybe 50 bits or something like that. Now, there is room for improvement of short package communications by challenging the way we do things. An example here is joint error detection and error control that we'll talk a little bit more about later. And other examples is, security and multiple access. So let's follow me down a rabbit hole. It's going to be fun, I promise, really. So here is a chain of processing that's normally done. So we start with some information bits on the top left, and then we go down through several steps until we reach the bottom where the channel is, where we actually transmit the radio wave. Okay. So the first thing to happen is that we have some data, some information bits that needs to be transmitted over the channel, and then we encrypt them, basically scrambling the bits such that an outsider cannot decode anything about the information bits. Okay. This typically just means shuffling around the bits, not adding bits to the message. The message is still the same length. Then we add an integrity tag to the ciphertext here. And the purpose of the integrity tag is to prevent manipulation of data when it's in transit. And there are other things also. But this is adding bits to the data that we need to transmit. And then there is error detection and error correction, which also adds parity bits to this message. And finally, there is a preamble added, and the preamble has metadata about the packet, maybe its modulation formats and so forth, the length of the packet and other things. It also contains training things for synchronization, channel state information, and so many things. What's important here is to say that the preamble, the integrity tag, and the CRC bits here, they are fixed fields of fixed length. Okay? And they don't scale with the number of information bits. However, the parity bits for error control here, they scale with the number of information bits. So a lot of work has gone into optimizing this. And that's why we have seen innovation in error control, going from convolutional codes to LDPC codes and polar codes right now. Okay, but when we have short packets, we have a problem because then the preamble, the integrity tag, and the CRC bits, the fixed fields here, could be on the same size as the information bits, or even longer. Right? A common integrity tag could be 128 bits, for instance. Maybe the information bits is only 60 or so. All right? So a tremendous overhead here. So the question is, can we do better here? And of course we can. Otherwise I wouldn't have had this talk, I guess. So let's focus on two things here: error detection and error correction. So the normal way is a busy slide, but if we on the top left here we have some bits. Let's call them K bits. Think of K as 100 or 50 or something like that. And then we have a number of possible messages, M messages, and M is of course 2 to the power of K. And then we send that through a CRC encoder to the, let's see if I can, here, no, we'll skip that. Anyways, we go through the CRC encoder, put some CRC check bits on this, we go to the error control encoder, we get some symbols, these are transmitted over the channel. The channel output is a noisy version of the input, and the error control decoder tries to fix the errors that have occurred on the channel, and the CRC check to the right inspects the data and declares it as being error-free or containing errors. So the output of the CRC check is either the data or a flag that says that the data was faulty. All right. So an undetected error, that occurs when the CRC check fails to detect an error that has occurred on the channel. And that's very, very serious, right? Because that data is then treated perhaps as the truth of the rest of the network, which could cause a disaster. So to keep the probability of undetected error low, we can do that by increasing the number of parity bits in the CRC, but that creates extra overhead, so we don't want to do that necessarily. And also, if the case is that the number of symbols we can put into the channel, small n here, if that is fixed, we have a budget here that we need to allocate to all things, to the information bits, to the CRC bits, to the error control, and so forth. So increasing the CRC parity bits is not a solution if we have a fixed n here, because then we would reduce throughput basically, because we will have more errors on the channel, more packets will be discarded at the receiver, and throughput goes down. Okay, so we have a trade-off here, and the question is, can we do better by joining the error detection and error correction blocks here? And we can, of course. So what we do then is the same basic diagram. We have K bits to the left. We feed them through an encoder. We get N symbols. Think of these as your QAM symbols. It's sent over the channel. And then the decoder is either outputting an estimate of the message which was transmitted or an error flag. Okay, so the detector can output an error flag or an estimate. And the errors are detected if the decoder says there is an error. An undetected error occurs when the decoder says, well, there is no error, but it outputs the wrong thing. So how can we visualize this? Well, in the gray box here, that's the space of all the outputs from the channel. So here's where all the output vectors can live. We divide that into 5 regions in this case. One region which is called R0, and R1, R2, and R3, and R4. So in this case, we have 2 bits to transmit. So we have 4 messages, and then we add another region. So we have one decision region for all the messages and one for declaring an error. Okay, so what's going to happen here? Suppose that the received vector falls into R0, then the decoder output is the error flag. If the received vector ends up in one of the decision regions, the other decision regions, in this case R4, then the output is that the fourth message was sent. Maybe 1-1, who knows. Okay, so in general, the decoder is then specified with these decision regions. And the trade-off between these regions would determine the probability of error and the probability of undetected error. So as an example, suppose we transmitted message number 1. Of course, the decoder doesn't know this, but this is what we transmitted. So ideally, we would like the received vector to end up in decision region 1, the green one here. So that would be the good thing. So no error occurs if the received vector is in the green region. A detected error is in the yellow region, and an undetected error is in the red region here. So green, good; yellow, it's not perfect, but it's better. Red is really bad. Okay. So what can we do then in the decoder? Well, we can of course increase the yellow region to make sure that we don't. What we want to do is to separate the regions, the green and the red regions, as much as possible, and we can do that by increasing the size of the yellow region. All right, we have two performance metrics, one which is the total error probability, and that's the probability of not being green, basically, so yellow or red. That's called the total error probability. The probability of undetected error is to be in the red regions. This is really what we want to avoid. And expanding the yellow region here will increase the total error probability because yellow will increase. But increasing yellow would also reduce green and red. Okay, so we would increase the probability of total error, but we will decrease the probability of undetected error. But again, if we have a lot of we also want throughput here. So basically what I want to say, we have a trade-off between total and undetected error probability. We need to strike it in a good way. So just to give you an example of this setup here, there is something called the CCSDS, Satellite Telecommunications Telecommand Standard. That was also difficult to say. But it has 64 bits that needs to be transmitted in 128 symbols. The probability of the total error probability, ET, should be less than 10 to the minus 4, and the probability of undetected error should be less than 10 to the minus 9. So which rules should we use then to optimize this? Okay, so Forney in 1968, a long time ago, actually knew how to do this. He says, well, compute the maximum likelihood decision and output that if it's good enough. Okay, so ML here is maximum likelihood and not machine learning. But the maximum likelihood output is basically looking at Y is given here, it's the output of the channel, so it checks for all the possible code words and outputs the one which has the maximum likelihood. And then if the maximum likelihood a code word has a likelihood which is much larger than the sum of the likelihoods for everyone else, if that's bigger than the threshold, then we accept the message as being error-free. Otherwise, we output an error. Okay, so this is the optimal way to do that. And this threshold then determines the trade-off between total error probability and probability of undetected error. Okay, the problem with this is that this rule is computationally infeasible to implement and also to analyze. Okay, and the reason for this is that the code here, the number of code words we need to check, could be, for a 100-bit message is 2 to the power 100, which is about 10 to the 30. Here, some industrial research will say, good luck with that. All right. So, what to do? Well, I have a paper here together with my co-authors, Alex, Gianluigi, and Balázs from Munich area, my former PhD student Uz, and my collaborator, colleague Giuseppe Durisi at Chalmers. So there is a paper here in Transactions of Communications. So what we did here is that we found bounds on this trade-off, which is better than is previously known, and this could be used then for benchmarking And then we tested these bounds towards some polar codes, and then try to evaluate how everything works here. So, okay, so how much time do I have? It says 6 minutes, 37 seconds here. Am I getting? Is it? Yeah. That's true? Okay, I'm in trouble. 10 minutes, okay. So anyways, we developed bounds, and we then looked at specific implementations using CRCs and polar codes. So all these bounds are achievability bounds, which means that the optimal method would be better than the bound. Okay. So general, also this is a lot of details, but basically what we can say is that we can compute two numbers, epsilon tilde t and epsilon u tilde, which are upper bounds on what is achievable. So there exists a scheme that can beat the bounds that we can compute. That is to have a total error probability less than the bound that we can compute, and a probability of undetected error which is less than the bound that we can compute. Okay, so so suppose we had a setup like this. We have BPSK over a Gaussian channel. We know that these error probabilities would reduce with SNR. And suppose we have some targets, so epsilon t star and epsilon u star that we would like to reach. And then the question is, what SNR is required to do this? That is, okay, but the problem is we don't know this. Nobody knows this. But we can compute bounds. And if the bound is less than the targets, then we know that there exists a scheme to do this. Okay, then we can look for that scheme. Okay, so what we want to find basically is an SNR threshold. So here is two curves. Here is SNR on the horizontal axis and error probability on the vertical one. And here is the curve for the total error probability bound. And here's the curve for the total, for the undetected error bounds. And we have two targets we want to reach, the target for the undetected error probability and total one, right? And then we increase SNR until both of these constraints are fulfilled. And we see we need about 3.4 dB in order to fulfill at the same time both of these. But it's a little bit overkill, right? Because we have then an undetected error probability which is much lower than the target. So we can do better. We can find a better scheme with a better trade-off. All right, so we then adjust the scheme a little bit. So we have the top left here, and then we go to the bottom here, and we basically flip the order of the curves. So this is still not good. So then we tinker around with the scheme a little bit again, and here we get like, okay, so this is the best we can do. This scheme barely fulfills the requirement at, SNR, which is slightly less than 3 dB. Okay, so that's what we call the SNR threshold. And we can plot this SNR threshold as a function of SNR, as a function of the number of symbols we can use in a packet. And the more symbols we can use in the packet, the better we can do. And we have three curves here. This is due to Forney in 1968, and these are our two new bounds here. And the bound is better if it's lower. Okay, so our two bounds is better than Forney's bound. Okay, so I'm gonna skip this. So we then took basically a standard scheme for with polar codes, which are then using CRC's aided polar codes, standard decoding algorithm, and then we fiddle around with the latest two blocks here in this, and we can get two new schemes which offer some flexibility in trading the total and the undetected error probability with each other. And then we plotted that towards the bounds. Okay, so again, here we have a bound on the SNR threshold that's given by Forney and our two bounds. And the lower bounds here, there are two ways of doing this, one which is called layered and one which is called thresholding. I don't go through the details here now. And then we had our scheme, practical scheme that we simulated. And the layered approach is these red crosses here, and the threshold is with the blue one here. So you see at very low short packets, there is a significant difference between these two. When the block length is a little bit bigger, there is no difference. Okay, but we're still far away from the bounds. So there is opportunity to do this much better. But, you know, we did some engineering approach and then we got these things. But we can do much better. We know this. So there is potential for improvement here. Yeah. Then we also wanted to see whether this is robust to channel estimation errors, because in the decoder we use channel state information, and we know that channel state information is never perfect. We can generalize our bounds to also handle this case, and then we get the following curves. Okay, so this is for QPSK over a channel where there is a random phase rotation, and then we use pilots in order to estimate that random phase, and then we plug that random this estimated phase into our algorithms, which assume that the phase is known, and then we get some result. So here with the bounds here, the two bounds we had actually now are more or less the same, okay? Which indicates that the layered approach and the threshold approach is basically they have the same bound at least, okay? Okay, and the problem here is also that the threshold method we had before, which was the better for low block lengths, is now the worst. Okay, so it's more sensitive to channel estimation errors. So again, these are the type of things one has to do. We try some crazy stuff on ideal situation, and then we implement more complexity in the problem, and we get different results here. So it turns out that this layered approach we have seems to be more robust to guess channel estimation errors than the threshold approach. But again, what we see here is that whatever we engineered here has a lot of potential to become better. So there is potential for better schemes here. So the bounds are still useful. Okay, and then I should say a few words about security here also. And basically that's important, okay? So then the question is, can we also implement security that's tailored to short block lengths in a reasonable way? And I think we can, but we haven't done it yet. We need to try some crazy stuff. I'll get back to you, okay? Then there is also a thing of massive random access when we have machine type communications. If we have many devices and small payloads, we run into this problem of have to be more efficient than what we are today. And here is there also some crazy stuff that we can try out. I won't be able to talk more about that today. Okay, so picking up from this rabbit hole and going back, I would say yes, we need 7G, and yes, it's time for academic people to start to think about that. We need to look at some crazy stuff also. We need to look at good stuff also, because we need to evolve 6G, but we also need to look at crazy stuff. I think we should always try to optimize sustainably. That is, to minimize resources subject to good enough performance. And I'm happy to say, when I chaired a session earlier this conference, this was exactly done, right? So minimize some resource subject to that performance was good enough. Okay, so that should be our paradigm. Short block lengths are important for machine type communications. And in this short block length regime, we should challenge the conventional truth, because they are not efficient in this regime. And there are many things one can look at: channel estimation, error control, error detection, security, multiple access, and so forth. Okay, so I will end there. Thank you so much. Thank you. Thank you.
Thank you, Erik, for showing the need for crazy stuff, especially in the challenge we have today. And I think you need that to get used of good enough. Allow me to say 30 seconds. If you look at the car industry, cars were sold many years ago for speed. No one sells a car today for speed, right? Cars are sold these days for energy, or consumption of power, whatever you want to call it. So fully agree with you.
Yes, thanks.
Sorry for my intermission. So the floor is open for questions. One question, please. Anyone? I don't see any. No? Okay, there's one there. Yes, thank you.
Thank you very much, Francesco Malandrino from CNR. I was curious about the bound work that you have presented. So the fact that the bound says that it is possible to achieve a certain performance. Does it also imply that there is a concrete algorithm, a concrete scheme that achieves that performance, or we do not get that type of guarantee? Thank you.
Okay, so if I interpret the question, so we have bounds now, and the question was whether we know if there is a scheme to achieve this. And yes, Forney's scheme would do this. Okay, the problem with Forney schemes is that it's not computable, right? But this is, if we go back maybe 30, 40 years, we didn't know how to reach channel capacity. Right? The codes we had then were far away from channel capacity. Now our codes are close to channel capacity. So with another 40 years of crazy stuff, we will find a scheme, I'm sure. Yeah. And Shannon knew how to approach to find a non-computable way to approach channel capacity. That was known for a long time. The practical scheme was not known.
Okay, so again, Erik will be around during the coffee break and the rest of the conference, so feel free to approach him and discuss the crazy stuff and the non-crazy stuff as well with Erik.
Yeah.
So thank you very much, Erik.
Thank you. Thank you. Good. So. Okay.
And before we finish, so as I was saying, an hour ago, whatever, not many people live to 100. Not many organizations live to 100. I'd even dare to say not in our area, that if you go back to 2G, there are many companies doing a lot of stuff that, okay, they are still there, some of them, but they no longer are involved in telecommunications. So, of course, it's a pleasure and an honor to have an habitué of this conference already. Peter has been on this stage, not this, but the equivalent one, for a number of editions already of EuCNC. And Bell Labs, Nokia Bell Labs, is celebrating 100 years. So Peter, please. Congratulations.
Thanks. Well, thanks to the organizers to give us a few minutes to share the excitement of 100 years Bell Labs, and I assume that the pictures will come up.
For 100 years, Bell Labs has been a pioneer of progress. We've harnessed our extraordinary imagination to fuel visionary breakthroughs and shape the future of technology, solving humanity's most pressing challenges. We created the first transistors and lasers, connected the world through the Telstar satellite, built the foundation for today's digital age with information theory, and developed artificial neural networks for machine learning. Our work has fundamentally changed how we live, work, and communicate. Today, as Nokia's Global Industrial Research Lab, we're setting the stage for the next century of limitless imagination, disruptive innovation, and real-world impact. We're unlocking the potential of responsible AI to transform networks and industries, solving the unsolvable problems with quantum technologies, advancing a 6G future to connect a hyper-digital world, giving us a sixth sense, and establishing the first cellular network on the moon to pave the way for a sustainable human presence in space. Nokia Bell Labs has made great change happen, and we're inventing the technologies that will define tomorrow.
Not sure that was part of the script, but nevertheless, can I now have the slides, please? Yep. One more. So while the slides hopefully at one moment will move. point here. Okay.
For 100 years,
No, this is not the one. Okay, this is the one. So you've been wearing these lanyards. You notice the emblem of 100s, but there's also the stylized ones and zeros. You've seen some of us walk around with these hoodies or T-shirts, and on the back there's also these stylized ones and zeros. They're actually digital code, and you probably have figured that they stand for 6G. And the code on my back actually says Nokia Bell Labs 100. So this is actually tribute to the Digital Information Society in which Bell Labs has made such important contributions. Claude Shannon was the first to use the word bit, and then the transistor is so foundational to the enabling of the digital infrastructure. Just think of this device, there's 10 billion of these transistors in here. The CCD camera invented at Bell Labs. Unix, the basis of the operating system. Neural networks, the basis of AI. And then cellular networks, also invented at Bell Labs in 1947, the same year as the transistor. So it's hard to imagine modern society, modern life, and this conference without the contributions of Bell Labs. And that led to many awards also. So these are the many inventions, and yes, it led to many awards, including 10 Nobel Prizes, 5 Turing Awards, and yes, also Grammy, Emmy, and an Oscar. But it's not only about celebrating the past, it's also a once-of-a-lifetime opportunity to put the spotlight on the research that we do today and how we shape the next 100 years. We're making important contributions to the future of 6G. An important part and a reason to have a next generation is enabling the new technologies of AI, creating a framework for innovations for the next 10 years from 2030 till 2040 across all the layers of the protocol stack. And we expect capacity increase every decade. It goes up by a factor of 10 in the wireless access network. And in some parts of the networks between data centers, the optical network, we expect the capacity needs to go up by a factor of 100. And we cannot allow that the energy consumption and the cost of that network goes up in the same amount. So that will require, use the words of Erik, crazy ideas to achieve these goals. And then also, how do you enable autonomous service creation across that network infrastructure? And we work towards a vision of the future network system, a unified networking experience that we intentionally call UNext. And then we also prepare for the quantum era, quantum computing, and we have, as a networking company, also research on quantum networks and quantum security, post-quantum encryption. But you may wonder, Bell Labs started in the US, but Europe has been an important part of the history of Bell Labs. The first Bell Labs location in Europe started actually in Utrecht in 1983. It was Arno Penzias, Nobel Prize winner, and then Vice President of Research, who said we need to globalize. And present day we have in Europe 6 locations, 6 main locations with Bell Labs research. And you recognize also how the different companies came together now in Nokia, and where research centers of those different companies like Alcatel, Lucent, Nokia Siemens, each integrated their corporate research centers now in Nokia Bell Labs. And we are very much part of the European framework programs since the very early days of RACE, throughout the different framework programs, and now an important part also in contributing to the 6G research. We are concluding the HexaX phase 2 at this event. We're seeing the first concepts of the Lighthouse project, Sustain 6G, and several other projects in SNS joint undertaking. We have many celebrations. In Murray Hill, we had already a very important celebration, and we will have that also in the other European sites. And when you have a birthday, you also reflect on the meaning of life, and that's what we, in a way, did. We had several Nobel Prize winners and Turing Award winners. Some of them came on stage in a panel session where we asked the question, what is it that made Bell Labs so unique? And to summarize it in 5 points, the very important first principle is solve a hard problem where there is a real human need. I mean, the search for the right problem defines you as a successful researcher. This is how you have the real impact. But then, as Erik also pointed out, stay grounded in the fundamentals, in the understanding of the fundamental limits of information theory or the fundamentals of physics. But then think crazy, think out of the box, don't go linear, and embrace the multidisciplinary approach. What the Nobel Prize winners and Turing Awards winners were all saying is the access to the intellectual resource under the same roof, or now virtually in the same organization of experts in different fields. A problem that is hard to solve maybe in your field may have already been solved in another field. And then another thing that they also pointed out is the freedom of research, but within strategic directional boundaries. So don't structure it too much into a project, because then you get what you ask for. Allow for open-ended research, because that's where the true innovation and new breakthroughs happen. So it was heartwarming to see that those were the principles that of the research cultures back in the days. And we call it research culture. What is that? A culture is the way we do the things around here. And that is true in a country, that is true in a religion, that is true in research as well. It are sets of practices that have survived the time and have been passed on generation to generation. And I'm happy to see that we still hold these high across the different research of the different generations of networks, and that we are now applying also for our 6G research. And that is well summed up in the next video, please.
For nearly a century, Nokia Bell Labs has been changing the world, one connection at a time.
Let's go!
1947, the first concept of a cellular network. We didn't just imagine it, we built it.
1.
From the first public 1G trials
2.
to connecting people across the globe. Then, we pioneered MIMO, enabling browsing on the go.
3.
3G networks, where the internet came to rival calls and texts.
4.
Until we invented massive MIMO, and data became the undisputed king of communications.
5.
Paving the way for today's 5G, ultra-fast data, low latency, and whole galaxies of devices connecting seamlessly. 5 strokes of genius. Or should we say, 6. Because Nokia Bell Labs is leading the way towards a 6G reality, towards an extrasensory network where the physical and the digital entwine. We have demonstrated more world firsts in wireless connectivity, from AI-native air interfaces that learn from their surroundings, to pioneering 6G networks that can intuitively sense objects and their movements. Nokia Bell Labs has taken wireless networks a long way since that first cellular concept, all the way to the moon, in fact. From one generation to the next, we have been the driving force behind how humanity connects, creating communications you can count on. All it takes is a few bits of imagination.
Thank you, Peter. Congratulations again for the centennial anniversary. So we ran a little bit into your coffee break. My apologies for that. We are closing the session now. Just two things, if you don't mind. So one, remember to go to the app and vote for the best booth. And if I dare to conclude this session, I would conclude it this way. Let's be bold, let's be wild. Let's make sure that 6G is about sustainability, providing good enough and not just going for everything we need, because then we cannot put in our bags. Let's be secure and take care of privacy and all these things. Hopefully we'll have a different radio interface for 6G. Hopefully we have a different network architecture for 6G, and we'll be here testing for 7G. Thank you guys for coming. Thank you very much.